Hello and welcome. In this video, we'll solve some problems on types of relations. So let us consider this problem. So problem says we have a set A with three elements 1, comma 2, comma 3, and a relation R is defined on this set, and the ordered pairs are 1, comma 1, 2, comma 2, 3, comma 3, and 1, comma 3. So the question is, how many ordered pairs should be added to this R to make it a smallest equivalence relation? So we can say a relation R is equivalence relation. A relation R is equivalence relation if it is symmetric. Okay, first we'll see if it is reflexive, if it is symmetric and transitive. If it is reflexive as well as symmetric as well as transitive, then such relation is equivalence. So let us check for reflexive property, like whether all the elements, all the ordered pairs are present already in the relation so that it is reflexive, or we need or if any ordered pairs to be added to make it reflexive. So we know that this relation is reflexive when a when all the elements of A is paired to itself, like 1 should be paired with 1, 2 should be paired with 2, 3 should be paired with 3. So if all these are present, then it is reflexive. We can see here 1 is paired with 1, 2 is paired with 2, 3 is paired with 3. So it is already reflexive, so we need not to add any ordered pair to make it reflexive exclusively. It's already reflexive. So, and we'll see whether it is symmetric or not. If it is already symmetric, or if we need any ordered pair to be added to make it symmetric. So we know that relation is symmetric if A comma B is present in R, then B comma A should also be present in R. If there is no A comma B, then we need not to check whether it is symmetric or not. It is always symmetric if A comma B itself is not present. So here we have 1 comma 3. So to make it symmetric, I should add 3 comma 1 to this. So now it is symmetric because see the first three elements which are reflexive in nature, 1, 1, 2, 2, 3, 3. These are self-symmetric. We need not to check whether it is symmetric or not. These are all self-symmetric. To know what is self-symmetric, you can refer to the previous video. So whenever the ordered paired elements are similar, we need not to check for symmetric and transitivity, because they are self-symmetric and self-transitive. So now apart from this, we have 1 comma 3. To make it symmetric, I have to add 3 comma 1. So this is the one extra element I've added to prove symmetric property. Now let us check for transitive. We will say the relation is transitive when if A comma B and B comma C both are present. If both are present, then there should be A comma C in R. So again, I'm not going to check for 1, 1, 2, 2, 3, 3 because they are all self-transitive. So we'll check for this element. So we have 1 comma 3. We have 1 comma 3. I'll take it as A and B. So I'll check for any other ordered pair which starts with 3. So I'll take this 3 comma 1. So this is 3 comma 1. So now I'll make this is B, this is C. So now I have to check whether 1 comma 1 is there or not. If 1 comma 1 is not there, I have to add 1 comma 1 to make it transitive. But we already have 1 comma 1. So there is no need to add another ordered pair to make it transitive. So it is already transitive. So we added only one element, only one ordered pair to the existing relation, so to make it equivalence relation. So the answer is only one is enough. Now let's move on to the next problem. So now in this problem we have set A equals 1, 2 and 3. So how many equivalence relations can be formed from this set A? Okay, so we'll solve this. The first equivalence relation is A cross A, which is an universal relation. An universal relation. Universal relation is both. An universal relation is actually reflexive, symmetric, and transitive. This we have already seen in the previous videos. So universal relation is all the three. So it is equivalence. So we can consider this one possibility, one relation which is universal as equivalence relation. Second, we can take R equals. So for a relation to be equivalence, should be reflexive, symmetric, and transitive. So let me make this as reflexive first. 1 comma 2 comma 2 3 comma 3. So this is actually reflexive, and all the ordered pairs have similar elements inside the brackets. So these are self-symmetric and self-transitive as well. So this is also an equivalence relation. Now let us consider a few more examples like R equals. I have to make it reflexive before I move on to any other property. So I'll make it reflexive first. Then I'll do like this. We have elements 1, 2, and 3. I'll pair 1 with 2. So I'll take 1 comma 2. So now up to here it is reflexive, symmetric, and transitive. Since I've added one more element, so I have to make it symmetric as well as transitive. So to make it symmetric, I have to add 2 comma 1. So now, so 1 comma 2, 2 comma 1. This is my A, this is my B, this is B, this is C, as well as A it is. So A comma A comma B is there, B comma A is also there, so it is symmetric. And if you take this, or I'll do like this, B comma A. This is to prove symmetric property. Now I'll take the same thing 1 2 2 1. This has A, this has B, this is B, and this is C. And AC is 1 comma 1. This is AC. It's already there, so it is transitive as well. So this is also an equivalence relation. Now I'll take the fourth example. I'll take 1 comma 1. I have to make it reflexive. 2 comma 2, 3 comma 3. Now I had combined 1 comma 2 in the previous case. I'll combine 1 and 3 now. I'll combine 1 comma, I'll combine 1 comma 3, 1 comma 3. So since I've added 1 comma 3, I have to add 3 comma 1 to make it symmetric. Now in the previous, it is very similar to the previous case. It is transitive as well. So it is both. It is all reflexive, symmetric, and transitive. So it is an equivalence relation. I'll go to the fifth case. So R is 1 comma 1, 2 comma 2, 3 comma 3. So this is reflexive. I had combined 1 and 2 and 1 and 3 in the previous cases. Now I'll combine these two, 2 comma 3. Combine 2 comma 3. I'll combine 2 comma 3. So to make it symmetric, I have to add 3 comma 2. Now this is symmetric, obviously. Now we can check for transitivity. So this is my A, this is my B, this is B, and this is C. So A comma C is actually 2 comma 2, which is already present. So it is transitive as well. So it is equivalence relation. So there are no other combinations to show it as an equivalence relation. You can try. So the number of equivalence relation we can form out of set A 1 comma 2 3 is 5. It is 5. So make sure you include universal relation for this equivalent to form an equivalence relation. Next problem, we have a similar problem here. So we have set A. A is A comma B comma C, and the relation is given as A comma A, and I'll leave some space here. Write B comma C, and A comma B. So number of ordered pairs to be added in R to make R reflexive and transitive. So to make it reflexive, so every element of set A should be paired with itself. So A should be paired with A, B should be paired with B, C should be paired with C. A is already paired with A, so now we have to add B comma B and C comma C to make it reflexive. So now it is reflexive. For transitivity, I'll not check first three elements because they are all self-transitive. So for these two elements, we have A comma B, B comma C. So A comma B belongs to R, B comma C also belongs to R. A comma C should belong to R. So there is no A comma C. So I have to add A comma C to the relation R to make it transitive. A comma C. So the number of ordered pairs we have added is 1, 2, and 3, and we made it transitive. So option C is the right answer. Let's move on to the next problem. So we have relation R equals 3, 3, 5, 5, 9, 9, 12, 12. Okay, so this makes me these four makes reflexive. We have 5 comma 12, 3 comma 9, 3 comma 9, 3 comma 12, 3 comma 5. So we have to check whether it is an equivalence relation first. So on the set A side, we have to take set A. Set A is actually 3, 5, 9, and 12. So to make it equivalence, first we need to check whether it is reflexive. So 3 is paired with 3, 5 is paired with 5, 9 is paired with 9, 12 is paired with 12. So it is reflexive. It is reflexive. Let us check for transitivity, or before that we can check for symmetric. 5 comma 12 is there. 5 comma 12 is the member of R, but 12 comma 5 it's not a member of R, so it is not symmetric. Not symmetric. So this option is not correct, and we can also say option B is not correct because it is not symmetric. So let us check for transitivity. For transitivity, I will not check these four elements because they are self-transitive. So now I'll take 5 comma 12. So for the first element, 5 comma 12, I'll check whether any other element, any other ordered pair starts with 12 or not. So there is one ordered pair which starts with 12. So I can take this 12 comma 12. So this is A, B, B, and C. So 5 comma 12 is a member of R. 12 comma 12 is a member of R. Then I have to check whether A comma C is there in R or not. A comma C is again 5 comma 12. So what one note we can add here is whenever we are taking elements which are not common, that is these two are not common, we shall not check the presence of the second element in any other ordered pair which has common elements. So for example, here we have 5 comma 12. I'll not check transitivity with 12 comma 12. It is always transitive, so we'll not go backwards. So we'll only check whether 12 is present elsewhere. So 12 is not present anywhere after 5 comma 12. So we need not to check for the presence of, or we need not to check for the transitive property here because it is always transitive. Now we have 3 comma 9. 3 comma 9, so there are no elements which starts with 9 after this. So anyhow we have a 9 comma 9 because we avoid checking for these two elements because it is always transitive when we compare with the common elements like this. So and we have 3 comma 12. 3 comma 12, there is no element which starts with, there is no ordered pair which starts with 12, so we can avoid this also. So 3 comma 5, So there is okay, so we have 3 comma 5, and there is an ordered pair which starts with 5. So here we have, which is 5 comma 12. So now, so we need to check, this is A, this is B, this is B, this is C. We need to check for the presence of A comma C, which is 3 comma 12. Is 3 comma 12 present? Yeah, it is present. So now we can say it is transitive. It is transitive. So one thing you should note here, whenever I checked for 3 comma 9 or any other element here, there is no A comma B. There is no ordered pair which starts with B. After this, there is no element which starts with B. That is 9 comma any element. There is no element after this. So A comma B is a member of R, but B comma C is not a member of R. So here it is transitive. We need not to check whether A comma C is present or not. If both are present, A comma B and B comma C are present, only then we have to check for A comma C, the presence for A comma C. So this is actually reflexive, transitive, but not symmetric. So this is also not correct. Let's move on to the next problem. So we have another relation 1 1 2 2 3 3 1 2 2 3. Okay, we'll write everything once again. 1 comma 1, 2 comma 2, 3 comma 3. So this part makes it reflexive. Next we have 1 comma 2, 2 comma 3, 3 comma 2, 1 comma 3. So we'll check for we will check for 1 comma 2. It is set A is 1 2 and 3. So from these three we can say it is reflexive. All these are present. Now for symmetric, we'll check for first one. 1 2 is a member of R, but 2 1 is not a member of R. So one counter example is enough to disprove any property. So it is not symmetric. So it is not symmetric. And say it is not symmetric. For transitivity, we'll take first element, first ordered pair 1 comma 2. Let us check any ordered pair starts with 2 or not 2. So there is an ordered pair which starts with 2, which is 2 comma 3. So this is my A, this is B and C. We have to check whether A comma C is a member of R or not. A comma C is actually 1 comma 3. It is already there. So one example is not enough to say it is transitive or not. Now let us move on to the next element, which is 2 comma 3. So 2 comma 3 is there. We'll check for any other element which starts with 3. So we have 3 comma 2, which, so the second element is 3 in the first pair. So we have to check the other ordered pair where the first element is 3. So this is my A, B, B, C. Let's check for presence of A comma C. A comma C is 2 comma 2. 2 comma 2 is there. It is already there. So this is passed. This is passed. Now let us check for the next element, 3 comma 2. So we have 3 comma 2. Let us check whether any ordered pair starts with 2 or not. So we have an ordered pair 2 comma 3 here, 2 comma 3. So now A comma C is 3 comma 3. 3 comma 3 is also present. So this is also passed. Finally, we'll check with 1 comma 3. 1 comma 3. Let us check whether any element starts with 3 or not. So we have here 3 comma 2. So not only this ordered pair, there is an ordered pair which starts with 3 also as well, but we avoid checking this because there is no need to check whenever the elements are common. So here we are checking the last element, so 1 comma 3. We are checking any ordered pair starts with 3 or not. So there is an element 3 comma 2. Now A comma C is 1 comma 2. So this is A, this is C. 1 comma, is 1 comma 2 a member of R? Yeah, it is the member of R. So this is also passed. So we can surely say it is transitive. It is transitive. So the relation is reflexive. But not symmetric. This is true. Reflexive but not transitive is not correct. Symmetric and transitive is also not correct. Neither symmetric nor transitive is also not correct. So option A is correct. Next problem. Okay, this is an interesting problem. We have A is equal to 1, 2, 3. The relation R is only 1, 2. So clearly it is not reflexive. Clearly it is not reflexive because there is no 1, 1, 2, 2, 3, 3. It is also not symmetric. It's also not symmetric because 1, 2 is a member of R, but 2, 1 is not a member of R. So it is not symmetric. Transitivity, transitive will check for 1, 2. A, B is a member of R, but we don't have B, C. B, C is not a member of R. So this says that it is transitive. It is transitive because uh, to say any relation not transitive, we should be having both A, B and B, C. So here we have only A, B. So this is not sufficient for us to say it is not transitive. So this is transitive. Okay, thanks for watching.